Hello and welcome to another Let's Study video. Today we're going to be continuing on with learning the programming Windows 5th edition. Moving on to chapter 4 on an exercise and text output. And so we will continue on and read on. So in the previous chapter, covering Chapter 3, we explored the workings of a simple Windows 98 program that displayed a single line of text in the center of its window, or more precisely, the center of its client area. As we learned, the client area is that part of the total application window that is not taken up by the title bar, the window sizing border, and optionally the menu bar, toolbars, status bar, and scroll bars. In short, the client area is the part of the window on which the program is free to draw and deliver visual information to the user. You can do almost anything you want with your program's client area and anything, that is, except assume that it will be a particular size or that the size will remain constant while your program is running. If you are not accustomed to writing programs for a graphical windowing environment, these stipulations may come as a bit of a shock. You can't think in terms of a fixed number of 80 character lines. Your program must share the video display with other Windows programs. The Windows user controls how the program's windows are arranged on the screen. Although it is possible for a programmer to create a window of a fixed size, which might be appropriate for calculators or similar utilities, users are usually able to size application windows. Your program must accept the size it's given and do something reasonable with it. This works both ways. Just as your program may find itself with a client area barely large enough in which to say hello, it may also someday run on a big screen, high-resolution video system, and discover a client area large enough for 2 entire pages of text and plenty of closet space besides. Dealing intelligently with both eventualities is an important part of Windows programming. In this chapter, we will learn how a program displays something on the surface of its client area with more sophistication than it illustrated in the last chapter. When a program displays text or graphics in its client area, it is often said to be painting its client area. This chapter is about learning to paint. Although Windows has extensive graphics device interface (GDI) functions for displaying graphics, in this chapter I'll stick to displaying simple lines of text. I'll also ignore the various font faces and font sizes that Windows makes available and use only Windows' default system font. This may seem limiting, but it really isn't. The problems we will encounter and solve in this chapter apply to all Windows programming. When you display a combination of text and graphics, the character dimensions of Windows' default font often determine the dimensions of the graphics. Although this chapter is ostensibly about learning how to paint, it's really about learning the basics of device-independent programming. Windows programs can assume little about the size of their client areas or even the size of text characters. Instead, they must use the facilities that Windows provides to obtain information about the environment in which the program runs. So we have painting and repainting. In character mode environments, programs can generally write to any part of the video display. What the program puts on display will stay there and not mysteriously disappear. The program can then discard the information needed to recreate the screen display. In Windows, you can draw text and graphics only in the client area of your window, and you cannot be assured that what you put will remain there until the program specifically writes over it. For instance, the user may move another program's window on the screen so that it partially covers your application's window. Windows will not attempt to save the area of your window that the other program covers. When the program is moved away, Windows will request that your program repaint this portion of your client area. Windows is a message-driven system. Windows informs applications of various events by posting messages in the application's message queue or sending messages to the appropriate window procedure. Windows informs a window procedure that part of the Windows client area needs painting by posting a WM paint message. And we have here the WM paint message. Most Windows programs call the function update window during initialization in WinMain, shortly before entering the message loop. Windows takes this opportunity to send the window procedure its first WM paint message. This message informs the window procedure that the client area must be painted. Therefore, the window procedure should be ready at almost any time to process additional WM paint messages, and even to repaint the entire client area of the window if necessary. A window procedure receives a WM paint message whenever one of the following event occurs. A previously hidden area of the window is brought into view when a user moves a window or uncovers a window. The user resizes the window if the window class style has the CSH redraw and a CWV redraw bit set. The program uses the scroll window or scroll DC function to scroll part of its client area. And finally, the program uses the invalid rect or invalidate RNG function to explicitly regenerate a WM paint message. In some cases, when part of the client area is temporarily written over, Windows attempts to save an area of the display and restore it later. This is not always successful. Windows may sometimes post a WM paint message when Windows removes a dialog box or message box that was overlaying a part of the window, a menu is pulled down and then released, or a tooltip is displayed. In a few cases, Windows always saves the area of the display it overwrites and then restores it. This is the case whenever the mouse cursor is moved across the client area, an icon is dragged across the client area, and when dealing with the WM paint message requires that you alter the way you think about how you write to the video display. Your program should be structured so that it accumulates all the information necessary to paint the client area, but paints only on demand when Windows sends the window procedure a WM paint message. If your program needs to update its client area at some other time, it can force Windows to generate this WM paint message. This may seem a roundabout method of displaying something on screen, but the structure of your program will benefit from it. And we have a section on valid and invalid rectangles. Although a window procedure should be prepared to update the entire client area whenever it receives a WM paint message, it often needs to update only a smaller area, most often a rectangular area within the client area. This is most obvious when a dialog box overlies part of the client area. Repainting is required only for the rectangular area uncovered when the dialog box is removed. This area is known as an invalid region or update region. The presence of an invalid region in a client area is what prompts Windows to place a WM paint message in the application's message queue. Your window procedure receives a WM paint message only if part of your client area is invalid. Windows internally maintains a paint information structure for each window. This structure contains, among other information, the coordinates of the smallest rectangular that encompasses the invalid region. This is known as the invalid rectangle. If another region of the client area becomes invalid before the window procedure processes a pending WM paint message, Windows calculates a new invalid region and a new invalid rectangle that encompasses both areas and stores this updated information in the paint information structure. Windows does not place multiple WM Paint messages in the message queue. A window procedure can invalidate a rectangle in its own client area by calling invalid rect. If the message queue already contains a WM Paint message, Windows calculates a new invalid rectangle otherwise. It places the WM Paint message in the message queue. A window procedure can obtain the coordinates of the invalid rectangle when it receives a WM Paint message, as we'll see later in this chapter. It can also obtain these coordinates at any other time by calling getUpdateRect. After the window procedure calls begin_paint during the WM Paint message, the entire client area is validated. A program can also validate any rectangular area within the client area by calling the validateRect function. If this call has the effect of validating the entire invalid area, then any WM Paint message currently in the queue is removed. Now we have a section on the introduction to GDI. To paint the client area of your window, you use the Windows Graphics Device Interface (GDI) functions. Windows provides several GDI functions for writing text strings to the client area of the window. We've already encountered the draw text function in the last chapter, but the most commonly used text output function is undoubtedly text out. This function has the following format. We have text out, taking in parameters HTC, X, Y, PS text, I length. Text out writes a character string to the client area of the window. The PS text argument is a pointer to the character string, so pointer to string PS text, and I length is the length of string in characters. The X and Y arguments define the starting position of the character string in the client area. Tired. More details soon on how these work. The HTC argument is a handle to a device context, and it is an important part of GDI. Virtually every GDI function requires this handle as the first argument to the function. And we have the device context. The device context. A handle, you'll recall, is simply a number that Windows uses for internal reference to an object. You obtain the handle from Windows and then use the handle in other functions. The device context handle is your Windows passport to the GDI functions. With that device context handle, you're free to paint your client area and make it as beautiful or as ugly as you want. The device context, also called simply the DC, is just a data structure maintained internally by GDI. A device context is associated with a particular display device, such as a video display or a printer. For a video display, a device context is usually associated with a particular window on the display. Some of the values in the device context are graphics attributes. These attributes define some particulars of how GDI drawing functions work. With text out, for instance, the attributes of the device context determine the color of the text, the color of the text background, how the X coordinate and Y coordinate in the text out function are mapped to the client area of the window, and what the font Windows uses when displaying the text. When a program needs to paint, it must first obtain a handle to a device context. When you obtain this handle, Windows fills the internal device context structure with default attribute values. As you'll see in later chapters, you can change these defaults by calling various GDI functions. Other GDI functions let you obtain the current values of these attributes. Then, of course, there are still other GDI functions that let you actually paint the client area of your window. After a program has finished painting its client area, it should release the device context handle. When a program releases the handle is no longer valid and must not be used. The program should obtain the handle and release the handle during the processing of a single message, except for a device context called with a call to create DC, a function I won't discuss in this chapter. You should not keep a device context handle around from one message to another. Windows applications generally use two methods for getting a device context handle in preparation for painting a screen. We have getting a device context handle, method 1. You use this method when you process WM Paint messages. Two functions are involved, begin paint and end paint. These two functions require the handle to the window, which is passed to the window procedure as an argument, and the address of a structure variable of type paintStruct, which is defined in the winuser.h header file. Windows programmers usually name this structure variable PS and define it with the window procedure like so: paintStruct PS. While processing a WM Paint message, the window procedure first calls begin paint. The begin paint function generally causes the background of the invalid region to be erased in preparation for painting. The function also fills in the fields of the PS structure. The value returned from begin paint is the device context handle. This is commonly saved in a variable named HDC. You define this variable in your window procedure like so. We have HDC, HDC. The HDC data type is defined as a 32-bit unsigned integer. The program may then use GDI functions, such as textOut, that require the handle to the device context. A call to end paint releases the device context handle. Typically, processing the WM Paint message looks like this. We have a case, which was probably from the switch on the message, case WM Paint, where we set the variable for our handle to device context. Our HDC is equal to our begin paint, passing in our handle to our window, as well as a address of a paint structure, such that this is the gateway. This handle device context is our gateway to the GDI functions. And it looks like we begin the paint, we use some GDI functions in between, and then we finally end the paint, passing in, of course, the Windows handle and the same paint structure address that we used prior. The window procedure must call begin paint and end paint as a pair while processing the WM Paint message. If a window procedure does not process WM Paint messages, it must pass the WM Paint message to def window proc, which is the default window procedure located in Windows. Def window proc processes WM Paint messages with the following code. Okay, interesting. So this is how def window proc works. It begins the paint and it finishes painting, doing nothing. The sequence of begin paint and end paint calls with nothing in between validates the previously invalid region. So it isn't doing nothing. It's beginning painting and ending painting, which validates the WM Paint message and clears the WM Paint message from the queue. But don't do this. We have a case, WM Paint, in which case it does nothing but returns 0. Windows places a WM Paint message in the message queue because part of the client area is invalid. Unless you call begin paint and end paint or valid rect, Windows will not validate that area. Instead, Windows will send you another WM Paint message, and another, and another, and another. The paint information structure. Earlier I mentioned a paint information structure. that Windows maintains for each window. That's what paint structure is. The structure is defined as follows. We have a struct type defined as a paint struct, which contains a handle to device context, a boolean of erase, a rectangle paint. We have another boolean for restore, another boolean for incremental update, I think, and we have a byte for RGB reserved, which is some color. 32 bytes. Interesting. This is our paint struct. Windows fills in the fields of this structure when the program calls begin paint. Your program can use only the first 3 fields. The others are used internally by Windows. The HDC field is the handle to the device context. In a redundancy typical of Windows, the value returned from begin paint is also this device context handle. In most cases, ferase will be flagged to false, meaning that Windows has already erased the background of the invalid rectangle. This happens earlier in the begin paint function. If you want to do some customized background erasing in your window procedure, you can process the wm erase bkgnd message. Windows erases the background using the brush specified in the HBR background field of the Win class structure that you use when registering the window class during WinMain initialization. Many Windows programs specify a white brush for the window background. This is indicated when the brush sets up the fields of the window class structure with a statement like this. We have the Win class .hbr background member being assigned an HBrush of using our internal function called get stock object, and we're getting this white brush. However, if your program invalidates a rectangle of the client area by calling invalidate rect, the last argument of the function specifies whether you want the background erased. If the argument is false, that is 0, Windows will not erase the background and the ferase field of the paint structure will be true after you call begin paint. The RC paint field of the paint structure is a structure of type rect. As you learned in chapter 3, the rect structure defines a rectangle with 4 fields, named left, top, right, and bottom. The RC paint field in the paint struct defines the boundaries of the invalid rectangle, as shown in figure 4-1. The values are in units of pixels relative to the upper left corner of the client area, and the invalid rectangle is the area that you should repaint. The RC paint structure The RC paint rectangle in paint struct is not only the invalid rectangle, it is also a clipping rectangle. This means that Windows restricts painting to within the clipping rectangle. More precisely, the invalid region is not rectangular. Windows restricts painting to within that region. To paint outside the update rectangle while processing the WM paint message, you must make this call: invalidate rect with our handle null true being passed in as parameters before calling begin paint. This invalidates the entire client area and causes begin paint to erase the background. A false value in the last argument would not erase the background. Whatever was there will stay. It is usually most convenient for a Windows program to simply repaint the entire client area whenever it receives a WM Paint message, regardless of the RC Paint structure. For example, if part of the display output in the client area includes a circle, but only part of the circle falls within the invalid rectangle, it makes little sense to draw only the invalid part of the circle. Draw the whole circle. When you use the device context handle returned from Begin Paint, Windows will not process outside the RC Paint rectangle anyway. In the Hello Win program of Chapter 2, we didn't care about invalid rectangles when processing the WM Paint message. If the area where the text was displayed happened to be within the invalid rectangle, draw text was sorted. If not, then at some point during the processing of the draw text call, Windows determined it didn't need to write anything on the display. But this determination takes time. A programmer concerned about performance and speed, and that includes all of us, I hope, will want to use the invalid rectangle during processing the WM Paint message to avoid unnecessary GDI calls. This is particularly important if painting requires accessing disk files such as bitmaps. Now we have getting a device context handle method 2. Although it is best to structure your program so that you can update the entire client area during the WM Paint message, you may also find it useful to paint part of the client area while processing messages other than WM Paint. Or you may need a device context handle for other purposes, such as obtaining information about the device context. To get a handle to the device context of the client area of the window, you call getDC to obtain the handle and release DC after you're done with it. Like Begin Paint and End Paint, the getDC and release DC functions should be called in pairs. When you call getDC while processing a message, you should call release DC before you exit the window procedure. Do not call getDC in one message and release DC in another. Unlike the device context handle returned from Begin Paint, the device context handle returned from getDC has a clipping rectangle equal to the entire client area. You can paint on any part of the client area, not merely on the invalid rectangle, if indeed there is an invalid rectangle. Unlike Begin Paint, getDC does not validate any invalid regions. If you need to validate the entire client area, you can call validRect with a context or a window handle. Generally, you use the getDC and release DC in response to keyboard messages, such as in a word processing program, or mouse messages, such as in a drawing program. This allows the program to draw on the client area in prompt reaction to the user's keyboard or mouse input without deliberately invalidating part of the client area to generate WM Paint messages. However, even if you paint during messages other than WM Paint, your program must still accumulate enough information to be able to update the display whenever you receive a WM Paint message. A function similar to getDC is getWindowDC. While getDC returns a device context handle for writing on the client area of the window, getWindowDC returns a device context handle that lets you write on the entire window. Ooh, interesting. Does that mean I'm able to write on the top bar? That'd be interesting. And that way I can finally get rid of the top bar in some of my programs that don't want it. A function similar to For example, your program can use the device context handle returned from getWindowDC to write on the Windows title bar. Woo! However, your program will also have to process WM and C Paint, non-client paint messages as well. Ooh, okay. Does this mean I can draw outside the client area? Those might be fun to draw. Text out, the details. Text out is the most common GDI function for displaying text. Its syntax is, text out with the handle device context, XY, PS text, and I length. Let's examine this function in more detail. The first argument is the handle to the device context and either the HDC value returned from getDC or the HDC value returned from beginPaint during processing a WMPaint message. The attributes of the device context control the characteristics of this displayed text. For instance, one attribute of the device context specifies the text color. The default color, we discover with some degree of comfort, is black. The device context also defines a text background color, and this is white. When a program writes text to a display, Windows uses this background color to fill in the rectangular space surrounding each character, called the character box. The text background color is not the same background you set while defining a Windows class. The background in the Windows class is a brush, and which is a pattern that may or may not be a pure color and that Windows uses to erase the client area. It is not part of the device context structure. When defining the Windows class structure, most Windows applications use white brush so that the default text background character in the default device context is the same color as the brush Windows uses to erase the background in the client area. The PS text argument is a pointer to a character string. An I length is the number of characters in the string. If PS text points to a Unicode character string, then the number of bytes in the string is double the I length value. The string should not contain any ASCII control characters such as carrier returns, line feeds, tabs, or backspaces. Windows displays these control characters as boxes or solid blocks. Text out does not recognize a 0 byte or, for Unicode, a 0 short integer as denoting the end of a string. The function uses the iLength argument to determine the string's length. The X and Y arguments to text out define the starting point of the character string within the client area. The X value is the horizontal position, the Y value is the vertical position. The upper left corner of the first character positioned at the coordinate point XY. In the default device context, the origin, that is the point at where X and Y both equal 0, is the upper left corner of the client area. If you use 0 values for X and Y in text out, the character string starts flush against the upper left corner of your client area. When you read the documentation of GDI drawing functions such as text out, you'll find that the coordinates passed to the function are usually documented as logical coordinates. What this means, we'll examine in more detail in Chapter 5. For now, be aware that Windows has a variety of mapping modes that govern how the logical coordinates specified in GDI drawing functions are translated into the physical pixel coordinates of the display. The mapping mode is defined in the device context. The default mapping mode is called mmText, using the identifier defined in the WinGDI.h header file. Under the mmText mapping mode, logical units are the same as physical units, which are pixels, relative to the upper left corner of the client area. Values of X increase as you move to the right of the client area, right in the client area. And values of Y increase as you move down the client area. The mmText coordinate system is identical to the coordinate system that Windows uses to define the invalid rectangle in the paint structure. Things are not quite as convenient with the other mapping modes, however. Here we have figure 4-2, which shows the X and Y coordinate of the MMM text mapping mode, where we have 0 of X and Y starting at the upper left corner of the client area, and increasing in value as we go to the right for X values, and increasing in values of Y as we go down the client area. The device context also defines a clipping region. As you've seen, the default clipping region is the entire client area for a device context handle obtained from getDC, and the invalid region for the device context handle obtained from begin_paint. When you call text out, Windows will not display any part of the character string that lies outside the clipping region. If a character is partially within the clipping region, Windows displays only a portion of the character inside the region. Writing outside the client area of your window isn't easy to do, so don't worry about doing it inadvertently. So this is interesting, okay? So writing outside the area isn't easy to do, but it's possible. Okay, that's good to know. The system font. The device context also defines the font that Windows uses the system font. The device context also defines the font that Windows uses when you call text out to display text. The default is a font called the system font, or using the identifier in the win.gdi.h header file, system_font. The system font is the font that Windows uses by default for text strings in title bars, menus, and dialog boxes. In the early days of Windows, the system font was a fixed pitched font, which means that all the characters had the same width, much like a typewriter. However, beginning with Windows 3.0, the system font became a variable pitch font, which means that different characters have different widths. A W is wider than an I, for example. It has been well established by studies in reading that text printed with variable pitch fonts is more readable than fixed pitch font text. It seems to have something to do with the letters being closer together, allowing the eyes and mind to more clearly see entire words rather than individual letters. As you might imagine, the change from fixed pitch fonts to variable pitch fonts broke a lot of early Windows code and required that programmers learn some new techniques for working with text. The system font is a raster font, which means that the characters are defined as blocks of pixels. In Chapter 17, we'll work with true type fonts, which are defined by scalable outlines. To a certain extent, the size of the characters in the system font is based on the size of the video display. The system font is designed to allow at least 25 lines of 80 character text to fit on the screen. The size of a character. To display multiple lines of text by using the text_out function, you need to know the dimensions of characters in the font. You can space successive lines in text based on the height of the characters. And you can space columns of text across the client area based on the average width of the characters. Now, what is the height and average width of characters in the system font? Well, I'm not going to tell you, or rather, I can't tell you. Or rather, I could tell you, but I might be wrong. The problem is that it all depends on the pixel size of the video display. Windows requires a minimum display size of 640 pixels by 480 pixels, but many users prefer 800 by 600 or 1024 by 768. In addition, for these larger display sizes, Windows allows users to select different size system fonts. Just as a program can determine information about the sizes or metrics of user interface items by calling the get system matrix. Just as a program can determine information about the sizes or matrix. Just as a program can determine information about the sizes or metrics of user interface items by calling the getSystemMetrics function, a program can determine font sizes by calling getTextMetrics. GetTextMetrics requires a handle to a device context because it returns information about the font currently selected in the device context. Windows copies the various values of text matrix into a structure of type text metric, defined in win.gdi.h header file. The text metric structure has 20 fields, but we're interested only in the first 7. And we have the struct text metric here with a TM height, ascent, descent, internal leading, external leading, average character width, and max character width. The values of these fields are in units that depend on the mapping mode currently selected for the device context. In the default device context, this mapping mode is text, so the dimensions are in units of pixels. To use the getTextMetrics function, you first need to define a structure variable commonly called TM, text metric TM. When you need to determine the text metrics, you get a handle to a device context and call getTextMetrics. We have HDC equals our getDC function, passing in our handle through our hwin handle. We have getTextMetrics with our handle to our device context and our text metric structure, and we have release DC. You can then examine the values in the text metric structure and probably save a few of them for future use. Text metrics. The details. The text metric structure provides various types of information about the font currently selected in the device context. However, the vertical size of a font is defined by only 5 fields of the structure, 4 of which are shown in Figure 4-3. The most important value is TM height, which is the sum of TM ascent and TM descent. These two values represent the maximum vertical extents of the characters in the font above and below the baseline. The term leading refers to space that a printer inserts between lines of text. In a text metric structure, internal leading is included in TM ascent, and thus in TM height. It is often the space in which accent marks appear. The TM internal leading field could be set to 0, in which case accented letters are made a little shorter so that the accent marks fit within the ascent of the character. The text metric structure also includes a field name called TM external leading, which is not included in TM height value. This is an amount of space that the designer of the font suggests be added between successive rows of displayed text. You can accept or reject the font designer's suggestion, including external leading, when spacing lines of text. In the system fonts I've encountered recently, the TM external leading has been 0, which is why I didn't include it in Figure 4-3. Despite my vow not to tell you the dimensions of a system font, Figure 4-3 is accurate for the system font that Windows uses by default for a 640 by 480 display. The text metric structure contains 2 fields that describe character widths. The TM ev char width field is a weighted average of lowercase characters, and TM max char width is the width of the widest characters in the font. For a fixed pitch font, these values are the same. The sample programs in this chapter will require another character width and the average width of uppercase letters. You can calculate this fairly accurately as 150% of TMAV car width. It's important to realize that the dimensions of a system font are dependent on the pixel size and the video display on which Windows runs, and in some cases on the system font size the user has selected. Windows provides a device-independent graphics interface, but you have to help. Don't write your Windows programs so that they guess at character dimensions. Don't hardcode any values. Use the get text metrics function to obtain this information. We have formatting text. Because the dimensions of the system font do not change during Windows session, you need to call get text metrics only once when your program executes. A good place to make this call is while processing the wm-create message in the Windows procedure. The wm-create message is the first message the window procedure receives. Windows calls your window procedure with a wm-create message when you call create window in WinMain. Suppose you're writing a Windows program that displays several lines of text running down your client area. You'll want to obtain values for the character width and height. Within the window procedure, you can define two variables to save the average character width, Ch4, and the total character height, Cy4. The prefix C added to the variable names stands for count. And in this case, a count of, or number of, pixels, in combination with X or Y. The prefix refers to a width or height. These variables are defined as static because they must be valid when the window procedure processes other messages, such as wm-paint, or you can define the variables globally outside any function. Here is the wm-create code to obtain the width and height of characters in the system font. So we have the case wm-create, in which case we grab our handle to our device context for our window, we get our text metrics, we store them, we take out the information for our count of our x pixels, our count of pixels in our x direction for the average character width, and the count of pixels for our height with the external leading field or spacing. And then we finally release our device context. Notice that I've included the TM external leading field in the calculation of Cy4. Even though this field is 0 in the system fonts I've seen lately, it should be included if it's ever non-zero because it makes for more readable line spacing. Each successive line of text is displayed. Cy4 pixels further down the window. You'll often find it necessary to display formatted numbers as well as simple character strings. As I discussed in Chapter 2, you can use the traditional tool for this job, the beloved printf function. But you can use sprintf and the Windows version of sprintf and wsprintf. These functions work just like the printf, except they put the formatted string into a character string. You could then use textout to write the string to display. Very conveniently, the value returned from sprintf and wsprintf is the length of the string. You can pass the value to textout as the I-length argument. This code shows typical wsprintf and textout combination. So we have an int I-length, we have a character, a Ch4 character array, a string terminated with 0. Buffer of 40 characters long. And the I length is our WSPrintf, where we're printing to this buffer using the text down there with the printf. And then we finally have our text out, which uses the buffer with the length of characters that we stored. For something as simple as this, you could dispense with the I length definition and combine the two statements into one. That's interesting. It ain't pretty, but it works. Now, putting it all together. Now we seem to have everything we need to write a simple program that displays multiple lines of text on the screen. We know how to get a handle to a device context during the WMPaint message. Now to use the text out function, and how to space text based on the size of a single character. The only thing left for us to do is display something interesting. In the previous chapter, we took a little peek at the interesting information available from the Windows getSystemMetrics function. The function returns information about the size of various graphical items in Windows, such as icons, cursors, title bars, and scroll bars. These sizes vary with the display adapter and driver. getSystemMetrics is an important function for achieving device-independent graphical output in your program. The function requires a single argument called an index. The index is of the 75 integer identifiers defined in the Windows header files. The number of identifiers has increased with each release of Windows. The programmer's documentation in Windows 1.0 listed only 26 of them. getSystemMetrics returns an integer, usually the size of the item specified in the argument. Now, let's write a program that displays some of the information available from the getSystemMetrics call in a single one line per item format. Working with this information is easier if we create a header file that defines an array of structures containing both the Windows header file identifiers for the getSystemMetrics index and the text we want to display for each value returned from the call. This header file is called sysmets.h. It is shown in figure 4-4. Okey-dokey. Okie dokie. So we're defining num lines to be an integer. This is the division of the size of the metrics data type divided by the size of the data type at array position 0. We have various system metrics listed here. We have texts shown down here. A great many of them. What is this slow machine processor flag? They call it potato. Your computer is potato. The program that displays this information is called sysmets1, and sysmets.s1.c source code file is shown in figure 4.5. Most of the code should look familiar by now. The code in WinMain is virtually identical to that in Hello Win, and much of the code in WinProc has already been discussed. Okay, looks like we have the function here. but not the function, but the whole program here in the source file. We have the sysmets.h, which we just looked at above here. In which case, let's try to program this. We'll open up Microsoft Visual Studio 2022. We're going to create a new project. This will be an empty Windows. Which one do we want? Windows Desktop Wizard. Next. We're going to call it the System Metrics. And we want this to be a desktop application and an empty project. We hit OK. And then we'll bring it up here. We're going to add our main.cpp file here. And so we're going to write this in C++. We don't need to write it in C. We could. Doesn't matter. Okay. Well, how about we write it in C then? If it doesn't matter. I'm going to just write this as sysmets1.c. And effectively, we just want to copy this over. And I imagine we're going to have to make some changes to get this to work. Just a few. Now sysmets.h, we don't have that, so we need to make that as well. So we go to our source files. No, header files, we add a new item. And we're going to write this, the sysmets.h file. We're going to go back up to our sysmets.h file as described in the book right here. We'll just copy this information in. Now that looks okay. Missed the comma. Bring this down here. And leave it like that. Okay, this is looking good. Okay, so that's what's happening. We have the system matrices, which is an array of this structure here, which I think is unnamed, but it has the I index, label, and description. So these are the I indexes, which these are defined in the winuser.h header file. So it looks like these are all of them here. This is it right here. So you have 43. Now, do we have 43 in here? 1, 2, 3, 4, 5, 6. I hate counting. We have 75 metrics, but only 43 down here. Oh, nope, there's more. And it looks like there's a couple more. A lot more. Okay. Interesting, like one for like a tablet PC or a server. Okay. I think that concludes the system.h. Copying that over. We'll save that, and we'll come back here. System.c. Let's copy in the Win API Win main function. It looks like a good copy. All right. Looks like a good copy. No issues. And looks like the last thing we need to do is simply copy over the window proc that we have defined here. I don't know what this 73 is. It's probably the page number. Yes, it is. We grabbed the page number on accident. There we go. That looks very nice. That was pretty painless. Copy over. Now let's look at what we copied over. Okay, standard Win main. We preemptively declare our window process up here so we can reference it here without defining it yet and define it later down here. We have our standard Win main taking in our H instances, a pointer to string of a command line, and our number of, well, int command show the type of opening status of our program. We set a character array, a Ch4 character array with the text sysmets1 to be our application name that we will reference later as our class name, as well as our caption name. And we create a handled variable with our window handle variable, a message handle, a window handle variable, a message variable, and a win class variable. This win class, we're going to define its members as a horizontal and vertical redrawing style window with our Windows procedure being referenced now. We're not going to assign any extra bytes in this example. We give it the H instance of our main function. We are going to load the basic icon for the IDE application icon, as well as the normal cursor of IDC arrow. Our background is going to be the white brush, so a perfectly white background. We're not going to have a menu, so we'll leave that null. And our class name is the app name, as well as a caption name. So they're all matching up together, so that we can, it was just some little bit of organization. We're going to register the class and check to make sure that it registers before we create a window with it. And we just exit the program if it doesn't fail to register, but it does give us a message box and lets us know that it failed. A little bit of debugging right there, or exception handling, I should say, of sorts. And then we finally create the window that we have defined up here with some with some more properties, which is the caption. Okay, so it looks like the caption is different. So it's actually get system metrics number 1, in which case we're passing in, we want the window style of a overlapped window, and we're going to use a default positioning and default width, as well as null for our menu and other stuff, but we do need to pass in the handle to our instance of this program. And finally, we want to show this window, And then we want to create our first WM Paint message using the update window to our Windows handle. And then we want to start our message loop while we're grabbing messages. So the first message we're going to grab and get message from the message. Well, this is going to send to the message queue. This message right here is going to create our WM create message. And then there might be more. But then we're certainly going to get the WM Paint message from this function right here. And then we're going to grab those messages here, translate them, and then dispatch them to our Windows procedure, which is just down there. Eventually, we're going to get a quit message, and we're going to get out of this while loop, and then we can return the W parameter of that message as an error code. So in our Windows procedure, we're going to define some variables that are going to be with every answering of our Windows proc, which we have some static integers, which these static integers mean that when we run Windows procedure and we set these values for a count of X pixels for a character, and X pixels for capitalized characters, or I guess that's the widest, and our size of the height of our characters in pixels. Once we set this, the next time we come into this window proc function, I believe because we have this static identifier here, that is going to be the same when we come back to this program. So if we don't, well, we won't have to change it or set it again. So once we set it here, it'll stay the same. So the first message we get is when we go to the create window function right here. That'll go here, and then we're going to get our handle to our device context using our Windows handle. And then we're going to run the function to get text metrics using our handle to device context, and we're going to be using the text metric TM structure. And then we have the CX, the character. So from the text metrics function and the structure that we stored that information we got with the function, we're going to store the important information for this program, which is we're storing the character drawing information, such as the average character width, the height, the pitch, I think, of capital letters, and then the height, plus the expected spacing or recommended spacing of vertical lines. Not vertical lines, but of lines of text. After we've used our handle to device context, we want to release it before we return 0 and exit the window proc. And the other message that we're going to get when we update the window here, this WM Paint message, we're going to create a new handle to our device context, and we're also going to begin painting using our handle to our window, as well as our paint as an address to a pointer or address to our paint structure up here. So this will be fresh every time we open up Windows procedure, whenever we come to this function. And then what we're going to do is we're going to iterate over the number of lines that we have defined, and now these num lines were defined in systemmets.h up here. So these are the number of lines, which is the size of the system metrics divided by the system metrics first integer, well, first structure. So this structure here, defined with the variable sizes int, the size of int, the size of two Ch4 pointers, and an int is our size here as well, and we want to divide that by the system metrics, the total size of the system metrics. So effectively is the total size of the array divided by the size of one of the first element, and converted into an int, or should I say cast to an int, is the number of lines that we're going to draw. So effectively one per each one of these. And so what we have is we have a text, a label, and then as well as a description. So then we have down here we using the text out functions, which take in our handle to a device context. And we have 0, 22, 22 plus CX caps 40 CX here. So bit complicated in some magic numbers. What is these 22? What is this 40? What is these magic numbers? These are magic numbers. This is not good. What is 22? You tell me. What is 22? I'm not quite sure. Let's see if this program even looks right before we start talking about this magic number. All right. Well, it looks perfectly good, I guess. Okay, so it's not full. But here we are. Okay, so look all the system metrics that we have available to us. All right. So that looks good. Okay. This talks about the Windows procedure, not enough room, and then we get into scroll bars. Okay, so I'm going to stop it here. Looks like we got a good thing here going. Now, I wonder what this is. Yeah, what is these what are the magic numbers of 22 and 40? I think I'll take a look at that and perhaps talk about it in the next video. Thank you for watching this Let's Study video, and hopefully is helpful to you.